Hey there, everyone. Welcome to the Chapter 4, Section 5 notes. This is a second video on Chapter 4, Section 5. I'm talking about graphs of nonlinear systems in this section. And in this video, I'm going to talk to you about a motion graph. So here we have a graph of a soccer kick. And so I'm going to talk to you about how I got the answers, how I wrote the functions for that, and then how I got information from that using the Ti-Nspire. So that's why everything's filled out already, because I'm going to be showing you stuff on the Inspire here. So let's talk about this. The graph shows the height, y in feet of a soccer ball, x seconds after it is kicked from the base of a hill with an initial velocity of 35 feet per second. The linear function represents a hill with a constant slope. So we kicked the soccer ball, it went in the air, and then it hit the ground upwards on the hill. So this line is our hill. So the first questions I asked are, or the first question I asked is, what is the function of each graph? The quadratic, I got this, and the linear, I got this. So let me talk to you about how I got that. So if I'm looking at a motion graph of a parabola, I'm going to use this model or this formula right here. Y equals negative 16x squared plus v naught x plus h naught. Okay, so negative 16 comes from the speed of gravity. It's approximately negative 16 feet per second squared. The reason why it's negative is because gravity is an opposing force. It pulls things down, so it'll always be negative. And so if you're using feet, you'll always have a negative 16 by the x squared. That's not a variable. I know x is your variable, but the negative 16 is part of the formula. It's there. It's going to stay there. Okay, so v naught x is what we're going to plug in for initial velocity. So we'll always put an x by v naught. And then by h naught, that's your initial height. Okay, so wherever we started from, wherever we kicked the ball from, is our initial height. All right, so right here I wrote negative 16x squared plus 35x plus 0. That's because negative 16x squared was from the formula. The plus 35x, that's my initial velocity. See, it was given to me in the word problem. So I just put 35 right there by the x. And then I wrote plus 0. Why did I write plus 0? That's my initial height, right? I bolded this. It's kicked from the base of a hill. The base of the hill would be at 0, 0. So that's why I wrote plus 0. Do you have to write plus 0? No, of course not. But I just thought I'd write it because it's the notes. Okay, so let's talk about how I got the linear function, y equals x. Well, you know, when you're writing linear equations, you're going to use y equals mx plus b to write your linear functions. So m would be your slope, that's your rate of change, that's your rise over your run or your pattern. And then b is where you began, it's your y-intercept. So if I look at the y-intercept of this, it starts at 0, 0. So the y-intercept was 0. So it would say like plus 0 right here, but I chose not to write the plus 0. And then there's no number in front of x for the m, so that means that m is 1, y equals 1x, because anytime there's not a number in front of the x, it's understood that there's a 1 there, because we're looking at 1x right here, right? So that means my slope was 1, and if I were going to write it as a fraction, I'd write it as 1 over 1. And so you can tell that because it goes from 0, 0, 1, 1. If you look at 2, 2, comma, 2. See, this is counting by twos, 2, 4, 6, 8. So it goes 0, 0, 1, 1, 2, 2. It's at a constant rate, so it's going to go 3, 3, 4, 4, 5, 5. In other words, it's going up 1 over 1, up 1 over 1. So that's a graph of y equals x. Okay? So what you're going to do is you're going to plug these into your graphing calculator. So I'm going to go to my add graphs page, and then you do not have to type in the y equals. You just have to type in the numbers, negative 16x squared plus 35x. And if you type in the 0, it's not a big deal because plus 0 doesn't change anything. So I'll just type in the plus 0. And then the other one would just be x for y equals x. The reason why you, the reason why I don't want you typing in the y equals, because you know you can. If you delete the equal sign and then you select y equals or a relation, let's just say I did y equals x. You see the graphs are identical because they should be. But you cannot look at the table. So if you do Control T, I cannot look at the table of any relation. But if I do Control T here, I can look at the table. And the benefits of looking at the tables is it helps you check your work. So, like in this graph, like let's say I want to be sure that I didn't make a mistake. I should be able to see points on this graph in this table. So, looking at the parabola, there's 0, 0, 119, and then at 2, it is at 6. Okay, so 2 comma 6. So I should see those 3 points, 0, 0, 119, 2, 6. So that's an easy way to check myself. I know I wrote the correct function because I see those points on the graph in the table, and I couldn't do that if I did the relation. All right, same thing for the y equals x. We said it was at 0, 0, 1, 1, 2, 2, 3, 3, and it's doing that. This skinny column here is the x column, so 0, 0, 1, 1, 2, 2, 3, 3, and so on. So yeah, check the table. It's helpful. So how did I get 2.13 seconds? Well, the question is, how many seconds does a ball, after how many seconds does the ball land on the hill? So that means I kicked it and then it hit here, the hill. So that's the intersection of the two graphs. So we're gonna do menu 6.4, analyze the intersection. So menu 6.4. We don't have to do this intersection right here, so you can just click somewhere here and then highlight that intersection. I got 2.13 comma 2.13. So your x is your time and your y is your height. How do I know that? Well, two reasons. The first sentence said the graph shows the height y and x seconds, okay? And then it's also labeled. X is labeled time, y is labeled height. So yeah. So in other words, after how many seconds does the ball land on the hill? 2.13 seconds. Now this is the same number, but that's not always going to be the case. So what's the height of the hill? So the hill's going up, right? So the hill is 2.13 feet high because I just look at the y coordinate at this point. So it's 2.13 feet higher than it was down here, right? Okay, so that's all there is to that. Just menu 6.4, the intersection of these two lines or these two graphs. So what is the max height of the kicked ball? 1.1 comma 19 is not the max height, and if you look, it's a little bit, it's close to it, but it's not exactly it. So this point given here is not the vertex. How do I find the vertex of the graph? Well, vertex of a parabola that's opening down is menu 6.3. If it were opening up, you do menu 6.2. So I'm going to go menu, analyze, and see. I'd find the minimum if the graph's opening down, making a U, but it's not making a U. Or graph opening up, I mean. This graph's opening down, so find the maximum. And it does say max height, so that makes it easier, right? And then it says graph. So don't click the linear graph, click the parabola, and click somewhere, highlight, make sure. We can't really see the maximum right now, but we know it's going to be somewhere in here. So I just kind of highlight the whole graph. And you see the point is at 1.09 comma 19.1. This is my time. This is the height. So the max height was 19.1 feet. How long did it take for the ball to reach its max height? Look at the time, 1.09, and that's it. Okay, so that's really all I wanted to go over on this video was, using this model to write your function. You've seen linear functions before, so this was the main focus of it. And then, of course, make sure you know how to answer questions that are, analyzing the graph. So menu 6.4, menu 6.3 is what I use. So thank you for watching, and goodbye.